duel makes a great demonstration of the ideal gas laws. Inside each of these peeps is trapped a bunch of air as well as some water that's keeping it moist. When we stick them in the microwave, that trapped air is going to expand. This is Charles's law. And the water is going to evaporate, giving you more gas molecules, causing further expansion. This is Avogadro's law. And when this happens, this is all going to make these peeps expand, and if you stick a little toothpick in them, maybe a cool sword-shaped one, they're going to duel one another. But as soon as you turn off the microwave, it gets cool again, the air is going to compress again, the volume decreases, and your poor little peeps are now just play toys. After they cool down a little so you don't burn yourself, and you can see all those little pockets of air that were expanded when we turned on the microwave. Now peeps, the science behind what's going on.
There are a lot of elements and types of different molecules, but the ideal gas law tells us that when these are in their gas state, we can be lazy when we think about them. Basically, in a gas form, the molecules are so far apart from one another, they're whizzing around, they don't even know the others exist. So we could pretend like they're kind of whatever gas molecule we want. They're just kind of like points. They're kind of like stars in the sky rather than these interacting molecules. And so the actual identity of that gas doesn't matter. They all behave the same, at least ideally and on paper. This is good enough approximation for us when we're talking about candy, though. And so we're going to be using Peeps as an example of how we can see the ideal gas law at work. Why Peeps allow us to do that is because inside of those Peeps, in addition to all of that gooey goodness, that's sugar and that gelatin that we'll talk about in a minute, there's a lot of air, and this air is going to be what makes them all fluffy. And then there's also going to be water, which is what makes them moist. And both the air and the water are going to play important roles in demonstrating the ideal gas law. What's going to happen is that inside of the Peep, when they make them, they whip in a bunch of air. And so there's all these air bubbles. And what's going to happen is that when you microwave the Peep, you're adding heat. You're giving those you're giving those gas molecules that are trapped in the Peep energy. And this energy is going to make them kind of want to try to escape the Peep. And when they try to escape the Peep, they're going to get farther away from one another. When they get farther away from one another, the volume's increasing. The volume of our Peep is going to be increasing. And this is a relationship of something called Charles's law, which is just one of the ways that we can rearrange this equation, this ideal gas law, which tells us that there's this constant relationship between the pressure, the volume, the number of gas molecules, and the temperature, as well as the gas constant, which stays constant. And so basically what happens is that if you change one thing, you're going to have to change at least one other thing in order to compensate and keep this constant. If you change one thing on one side of the equation, then something on the other side of the equation is going to have to directly change in the same direction. So if you have one thing get bigger on one side, then something has to get bigger on the other side. And if they're on the same side, if you have one thing get bigger, the other thing has to get smaller. And so what happens is if we increase the temperature, we're going to, if we keep the volume. So what's going to happen is if we increase the temperature, but we keep the pressure and the number of gas molecules constant, we're going to be increasing the volume. And this is what we see when we see Charles's law. And we can see this in action in the case of our Peeps. We're also going to be seeing Avogadro's law. In Avogadro's law, what we're keeping constant is the pressure and the temperature. And instead, we're allowing the number of gas molecules to change. And if we increase the number of gas molecules, we're going to increase the volume because they're directly proportional to one another. That's what this little like fish symbol represents. And so how are we increasing the number of gas molecules? We're doing this because of all that water that was in the marshmallow. As you give that water energy, the water is going to evaporate. It's going to be turning into a gas form. And we'll talk more about this in a minute. But basically, as you have these water molecules evaporate, they're going to be joining into those bubbles. So it's easier for them, the bubbles kind of make it so that there's pockets that the water can escape into and form a gas more easily. And so when it does so, it joins into these bubbles. You're getting more gas molecules in those bubbles. And when you have more gas molecules in those bubbles, then you're going to be increasing the volume. Because remember, in a gas, you kind of have everything evenly spread out in a way. And so if you have more things, then you're going to have to take up more space in order to keep that constant relationship between how far apart the molecules are from one another. And so this is going to be an example of Avogadro's law at play. Now, if the name Avogadro sounds familiar to you, and not just because it sounds like avocado, you might be thinking of the Avogadro's number or Avogadro's constant, which is going to be something that comes up when we talk about molarity. So a mole is kind of like a biochemist dozen, except that instead of meaning 12 of something, it means 6 times 10 to the 23rd of something. And that 6 times 10 to the 23rd is Avogadro's number. And so it's the same Avogadro, yes, and also that's can help you remember which one is Avogadro's law. It's the one that deals with the number of molecules, just like molarity and moles deal with the number of molecules or the number of things. And so Avogadro's law is telling us that as we add more gas molecules, we're going to be increasing the volume. So both by increasing the number of gas molecules and by increasing the temperature, so increasing the energy of those gas molecules, we can get this Peeps to expand. And this is going to be exploiting those bubbles that were whipped into the Peep. And now what's going to happen is that if you were to remove them from the microwave, you can play with them, but wait till they cool down a little because they're going to be really, really hot. But what you're going to find is you only have a little window of time before you can play with them before they get all hard. Because what's going to happen is not only are the water molecules, some of them escaping into those bubbles, but some of them are actually going to be evaporating all the way out of the Peep. They're going to be joining the mass of air instead of just being trapped in an air bubble inside of the Peep. So you're going to be losing all that nice moisture and you're going to get this kind of like hard shell of a Peep, which isn't that fun to play with anymore. So let's go in a little more detail. What is all that gooey stuff made of? That gooey stuff is basically sugar, water, corn syrup, and gelatin whipped together to trap in air. Gelatin, if you're wondering, it's basically just this chopped up mixture of collagen, which is that same protein that gives your skin its strength. And this protein's pretty cool, and I have more on it in my post on proline, which is one of the amino acids, so one of the protein building blocks. And it gets modified by vitamin C, and so there's this connection with scurvy. And if you want to know more about it, check out that proline post, but I don't want to get too off track here. The gelatin plays a role, though, in our Peeps because in addition to kind of giving the contributing to the texture and stuff, it's going to be allowing us to trap in all those air bubbles through that whipping up process. And it's those trapped air bubbles that are going to set the stage for what happens when we microwave things, both by giving us gas molecules in there already and by making it easier for the water to escape into those bubbles. So when we talk about water escaping from a liquid to a gas, we're talking about a form of evaporation. So whether a molecule or whether an element or whatever is in the gas, the liquid, or the solid form depends on how much energy those molecules have and how attracted they are to one another. The more energy the molecules have, so when we talk about energy, we're talking about typically temperature. So as you increase the temperature, what it means is you're giving the molecules more energy. And the more energy they have, the more likely they are to be able to escape their attractions from one another. But the stronger their attractions to one another are, the harder it is going to be to escape those attractions. And when you can't escape those attractions, you can't move around much. Take water, for example. Water has these partly positive parts and these partly negative parts due to its polarity, and I talk much more about that in other posts. But for now, just know that the water molecules are kind of sticky for one another. And if they don't have much energy, then they're stuck to one another, and they can kind of like only vibrate in place. And this is what happens in a solid. If you give them a little more energy, now they can temporarily escape from one another, but before they can make it out, they get sucked in, they get trapped by another water molecule. So they can only kind of glide past one another. And this is what happens in a liquid. In a gas, now they have more energy, they can escape from one another more easily, and they can fully escape into that gas form. Well, remember, when we're in that gas form, we can kind of just pretend like they're whatever molecule we want. So even though that water is really sticky to one another, if it's in this gas state, it's kind of like it doesn't even know the other water molecules are out there. But in order to not know that the other water molecules are out there, it has to be in an environment where there's not a bunch of liquid water around. And so this is why it's easier for water to evaporate when it's on the surface rather than when it's like inside of a liquid or inside of a solid. And in the case of our peeps, what's going to be happening is we have those air pockets. We have those little bubbles where it's places like it's kind of like it's on the surface in that there's less water around to pull the water molecules back in when they escape to form that gas form. And so if it can escape into one of these bubbles, then it kind of has a little gas pocket where it's easier for it to stay a gas and not get sucked back into the liquid form. And so you're making it easier for the number of gas molecules to increase. And remember, when you increase the number of gas molecules, then you're going to be increasing the volume, which is what Avogadro's law was telling us. Now, there are a couple of other ways that we can talk about arranging this equation, this ideal gas law, that also may come up in various situations. These are Boyle's law and Gay-Lussac's law, which is also known as Amundsen's law. And both of these are going to be including changes in pressure or allowing for changes in pressure. When we're talking about our Peeps example, when we're talking about Avogadro's law and Charles's law, we're keeping the pressure constant. But now we're going to be allowing the pressure to change and changing either the volume or the temperature. In Gay-Lussac's law, we're keeping the volume constant and the number of gas molecules constant, but we're allowing the pressure and the temperature to change. And if one of them changes, the other one has to change. This is again one of those directly proportional relationships where we get that little fish symbol because they're on opposite sides of the equation. So in order to keep this whole thing constant, if we increase one of them, we have to increase the other. And if we decrease one of them, we have to decrease the other. And if we want to think about this more intuitively, basically this is telling us that if we increase the temperature, but we don't let the volume change, the same number of molecules are with more energy, they're going to have to do something with that energy. And if they can't like kind of move farther away from one another, they're going to try to move farther away from one another and end up just banging into the walls of a compartment, banging into one another, increasing the pressure. A way that you can see this is if you were to say stick your water bottle in on a hot day, maybe you leave it in the car and you come back and your water bottle is kind of really, really firm. Basically, the water bottle, there's not much give there, and so it might kind of crush out a little. All those little like creases in the water bottle might smooth out as the volume tries to expand a little. But what's going to happen is that the volume can't expand very much. And so then you reach this point where you're just dealing with Gay-Lussac's law, where the pressure is going to be increasing and the water molecules that evaporated are going to be putting more pressure onto the walls, the inside walls of that water bottle. And so it's going to get firm. This is a demonstration of Gay-Lussac's law. But then what happens is that when it cools down, the water bottle is going to shrink back up. Because as the temperature decreases, the pressure is going to have to decrease back as well. And finally, we have Boyle's law. And here we're seeing an inverse relationship. So we're seeing that the pressure is inversely related to the volume. As one of these gets bigger, then the other one is going to have to get smaller. And if one of these gets smaller, the other one is going to have to get bigger because these are on the same side of the equation in our ideal gas law. And so if all of this is staying constant, these are going to have to be inversely proportional to one another. So how can we think about this? Basically, if we don't increase the number of molecules, but we're increasing the volume, what's going to be happening is that those gas molecules, we have the same number of gas molecules, but they're going to be kind of spread out more. And if they're spread out more, they're going to have less opportunities to bang into one another, to bang into the walls of the container. So you're going to be having less pressure generated. So you're going to have a lower pressure at a larger volume. But if you decrease the volume, Basically, what's going to be happening is all those molecules are going to be squished together with one another and they're going to be banging together more. You're going to be increasing the pressure. Similarly, you can think of if you were to just increase the pressure, you would be squishing these molecules closer together, you would get a smaller volume. And so all of that is a demonstration of Boyle's law. But the main two laws we have at play in our Peeps example are those other two. So we have Charles's law, which says that as temperature increases, volume must increase as well. And so this is why all those gas molecules, when you heat up the Peeps, those gas molecules are going to get farther away from one another. Your Peep is going to expand. As they expand, they're making it easier and easier for Avogadro's law to come into play, where the water molecules, now seeing all those kind of air pockets they can escape to, and now they have more energy. They're going to evaporate. This is going to increase the number of gas molecules. As you increase the number of gas molecules, you're going to be increasing the volume. As you increase the volume, the Peeps gets bigger. But all of this is dependent on that temperature. And so when you remove the temperature, basically the Peep is going to deflate back down. And since you've evaporated out a bunch of that water, now it's not going to be moist anymore. But it's still fun to play with. But remember, after it cools down a little, because it's going to be really hot in the beginning and you can easily burn yourself. So don't burn yourself. But do have fun playing with these Peeps. And remember that it's demonstrating a couple of the ideal gas law rearrangements.